once it is finally ready, you have to go for design evaluation. Design evaluation means you have to see the design testing, and you have to see that how the intended needs for which you have designed the product is being So once the design is done, you go for the design communication and documentation, and definitely before starting people production, you go for computer aided process class. And after that, the production is done, you go for quality control, strategy, and then the product goes to the market. Then you again get the customer's feedback. So with the customer's feedback, your design is again modified, and that's how this process becomes a continuous process. Correct? So this prototyping, which is actually a part of design evaluation, you have to take first few components of the design and then do the testing on it. So this particular prototyping or model making is one of the important steps to finalize product. And this product design earlier people used to do it by still draft. Later people started talking about this soft prototyping, which has its own limitation because the limitation of solving these mathematical models which are based on certain abstractions. So the latest trend in this direction is the rapid prototyping, where we try to deposit layer by layer to consider in the design data. This started during early 1980s with the canonical growth from the design manufacturing. So the concept is very simple. If you want to see the concept of this product fabrication approaches, that is very simple. That if I want to produce a component like this, we are going to remove the repeating state, or we are going to take two pieces of drawing there, or you want to make a bulk of material and compress it in the die, or you can basically deposit the material from bottom to the top. So therefore, the process chain, if you want to see, that starts with the CAD model. In the beginning, just to start with, we go with the CAD model. After CAD model, you are going to do the slicing, and you are going to save this CAD model as an STL file. So let us discuss this here. The first step will be CAD modeling of the component. CAD model will be STL file. So that is the tessellated, and this tessellated file is used in software to slice the component. So basically, you are going to get the layer data. So this is a generation of layer model. We are basically soft definition of the digital definition of this layer to the bottom. Now after that, we are going to have the generation of physical models. So for which we need a 3D printer, and this 3D printer actually requires data which is being computed in another software. So this slice data is converted into the tool path and the later deposition path or the deposition path. Then the data operates with 3D printer. So once the 3D printer is being operated, you get the physical prototype, which is which comes out from the printer, and sometimes we will need that into the post process. So when the post process is going to finish it, then we are going to have this prototype which you have made, which will be tested. Tested, and we get the final prototype. So this is the typical process chain which is being followed. So you can see that the process starts with the CAD modeling, and the entire thing is actually digital. So that's why this additive manufacturing or 3D printing, whatever you call it, is one of the vehicle manufacturing process. So this is one example, like you want to use this component for making solid model. After making the solid model, you have tessellated various surfaces. The various surfaces which belong to this component, they have been used. They have been approximated by small triangle as shown in this particular diagram. That is known as respiration. Once it is being done, when you slice. Now the slicing, once you do, you basically get the nested polygons from water to the top. And this is again written in typical data format like SLC format or sterilized format. Nowadays, technology, lot of development is taken place in this area. Another call that is called AM file format, additive manufacturing file format. This additive manufacturing file format has a number of other auxiliary information. Like today, we are going to make components which are having mixed blend of colors. Information related to color, information related to density, because we are able to make components with variable continuous varying density. So all the auxiliary information which is other than the quantum information that is also being saved in AM file format. This is a new format that is called additive manufacturing file format. So after this, the generation of various scanning parts are included for the parts that we take, and then we go ahead with the deposition. So the deposition principles, like old classification used to be that we used to classify like liquid-based processes, solid-based processes, or solid-based processes. The modern classification I will show you little later. So the first process which was developed was stereolithography. After that, powder-based processes were developed, and this is the modern process was developed. So I will show you many modern processes also in my other presentation. So these are some certain post-processing steps that we need to do post-curing. We need to remove the support structure, and we need to improve the surface quality, which we can do by sampling policy or by coding. So what happens is that you are going to have CAD model, and you can convert it to the physical model in a very short time. Like this shot is not as short as 15 minutes or 20 minutes. It may be even 10 hours. Correct? Because if you really want to use this CAD model by some other rules, like for example injection molding or die casting, you need to make dies, you need to have number of fixtures which is to be planned for months, which is not required in this case, and in few hours time you can convert your digital CAD model to physical function. So this conversion may take few hours, maybe 5 hours, 10 hours, even sometimes larger companies take 24 hours and more than that also. That is also short, because if you want to do it with dies and pictures and many other things, that may even take months. So the various data format which can be used to drive the additive manufacturing, that I have also told you, 3D CAD converted to SQL, you can print it. You can have 2D data, 2D drawing data, which can be converted to 3D CAD, and you can make it to SQL and print it. The other two rules are another important rules, like point cloud data. So this is a reverse engineering approach. Like if I am having an existing object, that object can be reverse engineered by certain instruments which are called scanners. So you have 3D scanners. 3D scanners are either laser based or white light scanner, or sometimes we are having tactile point cloud data capturing machines which are scanners, tactile scanners. And once the point cloud data is captured, you are going to have the reverse engineering software which will use the point cloud data, and the point cloud data then can be converted into surface models and solid models. You can create a SQL file and print it. Now the other data acquired from MRI or CT scans. So this is the biomedical route for which the theme of your particular lecture series today, on which I have to talk now. So the data which can be acquired from MRI or CT scans that can be used further, process in certain software and you get SQL files which can be printed. So this is a very interesting rule, which is the biomedical computation rule, for which this printing process is something which is very interesting. So if you want to use this particular 3D printing processes as a prototyping tool, as a design function, you want to use it in the design function, then what do you see is that introduction of this as a product prototyping machine, a product prototyping tool, what do you see is that this new way of model manufacturing, it is having the potential to reduce the manufacturing lead time by as small as, that is sometimes 10%. So means if I have planned my product to be launched in market in 100 days, I can do it in 10 days also. So that is the kind of thing which can be done in this. So then we basically have variety of processes. I'll show you modern way of classification now. So the stereolithography, this was the first process. Actually, from here only the 3D printing process started. The first process which was known as stereolithography. Stereolithography is the process where we are trying to deposit material one particular layer by layer, and the material which is used for deposition is photosensitive resin. So the photosensitive resin is poured into the grid form and it will be spread like this, and then from the top the laser comes. The laser comes and uses the mirror. It deflects the laser beam, and the spot of the laser moves like this. So wherever the laser spot goes, below that liquid material, which is actually monomer resin, that converts into polymeric resin and it becomes hardened. We are able to actually deposit one layer. Then the platform again goes down, we pour more liquid and we try to again bring the laser spot scanning the surface, and then we keep on adding the material from bottom to the top. Then there is another one, which is instead of using liquid resin, we are using polymeric powder. So we can use polymeric powder in all the process which is laser sintering. We can use even the metal powder, that is powder bed fusion process. We call it selective laser melting. So if you are using plastic powder, it is called SLS. If you are using metal powder, it is called SLM, selective laser melting. But the principle is same, only the temperature ranges are going to be different. And of course, if you are using metals, then you need to maintain an argon gas environment. You have to maintain a gas environment, otherwise this material will oxidize and there will be oxidation and nitrization. So you have to be able to control the material property. So here what is being done is that you can understand from this picture. Then this entire process is carried out in an enclosed chamber in an atmosphere of nitrogen, or nitrogen in case of polymers, and argon or any other inert gas in case of metal. And in case of plastics, this chamber is maintained at temperature 2 degrees Celsius below the melting temperature of this polyethylene. So this powder is being spread by the reporter. Then powder gets exposed to laser beam. So this is how the laser beam comes. So if you just have a look here, that the powder, one layer of powder is being spread and the laser spot comes and moves here. Brown color is powder which is being solidified. Then next layer comes, we are reporting, the form moves down and we are reporting the next layer. So I believe this process is clear to everybody, that first you are spreading first layer, the laser comes from the top moves down and you are again spreading the next layer. So that's how this entire process works. Then this printer, I believe you might have already seen in your lab. This 3D printing is called full filament fabrication or full dimension modeling. Here, there is a spool of polymeric wire. So this polymeric wire is being drawn by two counter-rotating rods, and it comes down like this. So once it comes out, and there are heaters to melt the material. So once it comes out, it is a molten various material, and by using a XY movement, you are able to actually deposit this material like this. So generally in the printer you are having two nozzles. One is for the main material and another is for the support material. Okay, then so basically we are having some other processes also which are plastic processes, like what is called polyjet printing. So this polyjet printing is also taken over by the FDM now, that is specific systems. There is another machine called jet corp machine which was similar to it, and then SLA, Stereolithography, FDM and SLA. So for various features we are able to compare these processes, like in terms of accuracy, feature details, strength, surface quality, functionality, whether they are transparent or not, they are flexible or not, they are colored or not. So it is the polyjet process today which is able to actually make components with mixed colors. So millions of colors you can produce components with millions of colors you can use into a new polyjet process. So multiple colors within part. It is only the polyjet part that can be able to do it. That was a couple of jet car also. Now the latest system development in this field that has taken place is the metal printing, that is called direct energy deposition or directed energy deposition or direct metal deposition. So around 2006, the research took place at India National Laboratories of USA. They have developed this machine. But here, there is an organ through which the powder comes down from here, and it is suspended in argon gas, and the laser comes from here for the printer, and wherever the stream of the powder and the laser interact, it melts it spontaneously, and with XY movement you are able to deposit this material for the fixed form. So the various components which were deposited in the beginning stage of this development of this process are being shown here. So you can see that definitely you can deposit long and slender components. You are even able to deposit components with thicker walls, and you are able to deposit housings like this. But definitely the surface quality is not that very high in this case. So I'll show you some more videos when the things will become more clear for you. So here you can see that this is how the processing zone looks like for this process. So for this process, this is the processing, actual processing zone. So the laser is coming from the center, and the powder is coming like this, and this is how it looks like. So this example is about repairing of a one wheel. One component, you are able to deposit and repair the component also using this process. And this particular processing zone is about this particular process, about this process. So here, because we have spread the powder, and on this location where it is coming, so this is how the deposition has taken place. The one layer has been shown here. So finally, you are able to get the component like this with this process, which is having quite good surface quality, but the surface quality is really documented like this. It is not very high surface quality. So the applications if you want to see, the applications are in variety of fields. Like you can apply in design area where you can talk about proof of concept, visualization of objects. You can do it with analysis and planning. So for flow analysis, you can do the experimental flow analysis. You can do stress distribution study. You can make model, put it in the polarizer frame, which is the benchmark physical analysis. And there are biomedical applications which are large level. So these slides which are seen today, they were made in 2006. So 20-year-old slides aren't available. That's how new slides are transported. So this is something which I'm referring to for instance. Diagnostic and surgical operation planning, design and fabrication of custom prosthetics and implants. Those have already been planned or rather there was available literature at that time 20 years ago when these slides were created. So, but there was a lot of application in manufacturing and tooling. So we can create vacuum casting molds, we can create metal spring, we can do induction casting, die casting, etc. etc. So this is how in the field of manufacturing also we have a lot of applications. So this is the dimensional application slide. So how do things go? Like you all know about CT scan or MRI scan. And this is again a layer by layer. So it is basically in CT scan you are doing continuous X-ray. In X-ray you take one shot. But when you do CT scan, the shots are taken at an interval of 100 hundreds of shots are taken. So this is how it looks like. And these are the digital grayscale files. So these digital grayscale files they can be used in a software called reading for simple where the most important software or the software which was came in the market first software is image that is called materials is the company name and now some more softwares have been added. Simple layers of software. These types of things can be done in MATLAB also. MATLAB, if you want to do, you should do a lot of programming. So you need to import this background file, digital file into the software, and then you can reconstruct the digital model. So the model will look like this. And then this is, you can import it as a, export it as an STL file, which can be used to slice and you can operate it in the printer, or you can create these kinds of models. And this is one of the important applications, and of course the potential of this 3D printing is best utilized by the biomedical applications. The different products if you want to see convenient manifolds, these are the walls printed by SLS process, electronic packaging, medical implants. And the geometry is like this if you want to do it. Imagine that there is no other manufacturing process which can do this. So, in every circumstance, you will not find that I advise that technical manufacturing should be used. But definitely there are situations like this when you cannot do this component, because you cannot produce this component without technical manufacturing. Now these are some material components. So this is a green implant to another implant which has been finished by aggressive flow conditioning process. This is another implant which has been made by metal layered manufacturing process. Then this is a rental implant which has been made by previous machine which is solid bed plated technology. Then some aerospace applications are there. So these blades can be produced by SLS process and also do the repairing by directed energy removal process. So titanium aerospace grade alloy that can be very well deposited and we can make components, we can repair components by this method. Then, like there are some very typical applications which have been shown here. Since the components are like this is a third column, it has some internal details also. You have these kinds of components, correct? So then what you see is that the components like this, there is no other choice other than doing the editing. So the component like this is called topologically optimized component. The topologically optimized component which can be done through additive manufacturing. This is a guide. And this is a die which has been produced by SLS process. And then we are coating it also with certain other coatings for improving the wear resistance. And you might have seen this vehicle. So this line, headline, is being produced by SLS process, plastic process directly. So here the SLS process has directly been used as a manufacturing process. So the electrical fittings are done, and then this is being sprayed by the metal spray paint. So after that, the complete assembly is being put here in this vehicle. So they are directly using it as a machine. So in case of plastic components, you can, if the component is quite large, you can print it in two parts also and join them, glue them. But it is not possible in case of metal components. In metal, you cannot do it. This is the finished and printed headline. Correct? So then you can also have certain very beautiful artifacts that can be produced by creative process. Correct? So now the next generation of additive manufacturing, rather this is a little older slide, you want to update it. But now already we have made some components and now also doing research by that, where we are embedding, these kinds of sensors by depositing in any implant or maybe any industrial component, which will beneficially service and then deliver some signal. Yes, so certain electronic circuit. So if there is any damage to the component or there is something is going to happen that component while it is under process, under action or under service, then the signal will change. As you know, that some track is going to take place, the vibration characteristics will change. So you get different kinds of signal pattern. Before hearing the catastrophic failure takes place, you will be able to diagnose in advance that there is likely to be failure soon. So you can repair the component, remove the change the component before you the failure takes place and everything stops in the shop floor. So that kind of smart component we can be produced by additive manufacturing by embedding different kinds of sensors into it. So like yesterday only I was listening one presentation from Apple University at an department. So one of my students in faculty said who is doing is trying to put these types of sensors in an implant so that when the bone is growing, they are able to understand that how much growth has taken place, how much stress is to be given. So that kind of smart implant that is we're trying to figure research, the concept like this is utilized in now for the next thing. So what you can see is part of the biomedical engineering. The applications are definitely very biomedical engineering, but there are very interesting applications and engineering also. Very engineering. So complexity of the objects being manufactured, of course the geometrical complexity of the objects being manufactured is not a limitation in 3D printing. So you can see this, like this is a monument. This has been scanned. After scanning, you are able to create a particular model of this monument. Still, if you see the challenges, you realize that the strength may be not as high as any folding or any compression molding in case of plastics. But definitely you can enhance it by proper planning, by optimizing parameters, or by blending certain additives or beauty fillers or making it composites. The surface quality is definitely inferior in engineering because you are depositing the material layer by layer. It's not like continuous manufacturing. So the surface quality is definitely going to be poor. You need to have do some chemistry treatment if you want to improve the surface quality. And accuracy is also low because the deposition takes place in an uncontrolled manner because you are depositing it and there is a free flow. It's not that the things are being thrown at a time, you are doing it at a time. In compression molding, there is a constricted or limited volume and the limits are known and you are pouring the material, pushing the material into it So the accuracy is very high. But here, once you're depositing, it becomes a little bit more, a little bit less because of the purity of the material, because of the heat conductivity of the laser is involved. So you will find that the accuracy is definitely, you cannot compare the accuracy the way when you do machining operations of the sub-micron accuracy. That is not possible in case of printing and casting. So I'm not going to do this. So let me now show you some other presentation. So just try to see this is another important presentation. This is still part that one. This is I think developed made during COVID period. So 4 or 5 years ago. So so this direct energy deposition, which was started in 2006, today it has gained a lot of advancement. And today we are having commercial systems available. The principle can be understood from here that you have these channels, so the powder is coming down, and there's a laser, so that's how you're depositing. Correct? So there's a video for it. You can just have a look on the video. So I think this basically is clear to all of you. Then sometimes the robots are also utilized for editing manufacturing, though not very dependent approach because sometimes these leads to very limited solutions. And still people have tried it. So these types of solutions are also illustrated. So you can just have a look on those that it's hard for directly melting material, mostly used with metal powders or bar switches. Material is melted using laser upon deposition. Then the thing is usually fast building. Quite dense part, no support structures are needed because we are using this 5 degree of freedom table and can be used for repairing. But poor surface quality, significant post processing and part complexity is needed, we have already explained. So this leading process, it has, you know, application in variety of fields, like the aerospace, automotive, avionics of components, nuclear technology, medical components, which is biomedical, industrial applications. Then LMP is also similar thing that deal with, yeah. Then let us talk about electron mechanical model. So the electron beam additive manufacturing, instead of using laser, they are using electron gun and very high power that is around 2 kilowatts. So, but the electrons can travel only in vacuum, so you have to maintain vacuum here. But this gives you a high quality components without impurity and they yield excellent reusable properties. So we made each layer of powder and it is designed one. So you can use powder bed fusion also and one can use a wire also. So both the variants are possible because the electron is available. So here we can see some components have been shown, which have been made by electron beam manufacturing and the variety of areas it has application. So medical is different, we can make reflective metal components, the mild glaze, corrosion components, so here resistant components are creating power resistance. Okay, then we have, hello, we have we can utilize welding process also that is known as wire art additive manufacturing to manufacture to do additive manufacturing. So there is a video once again, you can just have a look on this video. So this shows us how cold metal art transfer, CMT process or MIG, metal inert gun welding process can be used to deposit the material and make the quantum. So this is how we, operate deposit. Of course, we can visualize that we're doing by welding process. We're going to get what else. So that there are a lot of different distortions we need to make data. And sometimes we need to use stable gases also because reactive materials are being deposited. The resolution is very low, process quality is quite poor, and those should be required if you want to reduce these wire are this is some components which have been made by not the then let me talk about one more technology which is DLP, digital light processing. This is 3D printer which comes for only 3-4 lakh rupees nowadays. So it is the process is for polymers once again, and it is like a projector. There is no laser used. So DLP printers need a light projector like this. So the principle is like this. Like in SLS, we are using laser, which moves the spot moves into depositing. But here we are using a projector, which can do the entire layer in one go. So this is also a very nowadays this process is becoming quite popular. We can get it through that. Today you can get this within 1 lakh also, but not very expensive. Okay, then let me talk about the last thing, which is called two-photon polymerization technology. This is for biomedical application once again. Very typical biomedical applications are there. So here, what we are doing actually, we are depositing inside the monomer material. So, like in most of the 3D printing processes, whether it's powder or liquid, it is depositing on the top. But here, what is happening that this is the liquid, monomer liquid, and deposition is taking place here. So the nickel is filled and I'm depositing sometimes here. So when the laser spot is going there, it's resulting here, and the size of the laser spot is as small as 100 nanometers. So very fine detailing you can do. You can create components of micro sizes with nano features. So that kind of technology, very costly technology, because the high resolution of 100 nanometer, the technology is two-photon microscopy, online process operation is available. And now the best thing about it is that you can do polymerization in the presence of biological tissue and cells. So because the size of the biological tissue and cells is around 600 microns, 400 microns, but it works at a resolution of 100 nanometers. So you can do the deposition of proteins or any other things. So today those materials you cannot process, but one can visualize the situation by picture that we can do deposition of very small volumes within the tissues or within the cells, within the cells. So you need to have biocompatible initiator or materials, and you need to have water-based systems which do not react with it with low toxicity really bombarding biological applications. So there are a number of applications, and you can see some applications here that we can use it for micro optics. So these are certain crisps which when you develop by this method, the dimension you can observe. This is a lens, micro lens. You can see the dimension. And this is a cell biology. Scaffold. This scaffold, you can observe the kind of porosity that has been manufactured by two-photon polymerization. These are the micro needles for stainless blood delivery. So these are the needles for stainless blood delivery. Like you can see the mosquito, this is something like this. You don't feed it, but there's an injection of certain chemicals by the mosquito. The stainless matter can do these stainless blood delivery. So those types of needles are like this plant. Then I'll talk about now the last thing, that is composite printer. So today we are having composite printing that is readily available. A commercial printer called Mark IV is the name of the company. The principle is very much similar to FDM process. But here the material and their wires and what your screws which are shown here, they are supplied by their own. You cannot have your own because the printer is costly, the controls are very accurate, very nice finish. At the same time, material you cannot use your own components. So different kinds of materials are there, I'll show you. And the system is like this. So it comes out of the nozzle. You can deposit nylon, you can deposit carbon fiber, alternatively or a mix, and you have something called onyx material, which has a nylon and chalk fiber into it. So you have different types of spools are there, onyx, nylon, carbon fiber, fiberglass, Kevlar, HFSP fiberglass. Then their properties are there, and this is their tensile properties, flexural stress and flexural strain. So those have been shown here. And they have basically various kinds of infield and figure, etc., which can be used. And so this new composite printing, meeting of very practical and like other printers can be used for with other instance. Other printers, what happens is that suppose like power turns off. आपके कितना कंप्लीट बना लिया power चल रही है और खराब है. But in this printer you can start from there get from. That kind of facility is also there in this printer. And the disadvantages are that separate seal container is required for filament because it can catch fluidity, limited flexibility which you can use, and the materials are patented material. You cannot use your own materials. The company is not open source. That is another problem. So you can see some applications. Now this is a sharp absorber printed by onyx material. It can be used in a bike. The strength is so good. It is a soft job for holding purpose the machine. It's a carburetor which is being printed by this particular machine. So with this I am stopping here. Now I'll show you maybe one, two cases. If we have done a calculation, so you have seen so many things by now. Let me just tell you, the development today, where we are, today we are somewhere here. Correct? We have started with rapid tooling, rapid prototyping. We have gone for aerospace printing. We have gone for composite, and we are doing a lot of biomedical work now. And we are somewhere in 26. But another next 10 years target is that we want to create or fabricate full body functional organs. Correct? We want to create body parts, which are functional body parts. By the use of 3D printing, taking biomaterials, using machine engineering, and making them alive. That is the target. This is what we are looking for the next 10 years in the area of 3D printing. Correct? So, today if you see, now in classification, we have shown so many things, correct? In the modern classification, if you want to see of additive manufacturing, we have the 7 categories in which the processes are. That collaboration of sodium, SLA, and CFC. Material jetting, binder jetting, material extrusion in LDM, sheet metal lamination, powder bed fusion, SLS process, and directed energy deposition. These all things are typical modern classification of additive manufacturing process. This all I have already told you. Printing engineering also, people are printing bridges. People are printing different structures also using this particular methodology, and you can make customized foods also using this methodology. इतना प्रोटीन डालना, इतना कार्बोहाइड्रेट डालना, इतना ये डालना, इसका वो डालना, those kinds of things can also be done in food. So, let me show you that in Additive we have done some biomedical engineering work. So we have done this. We have developed our own printer that is pattern deposit in stents, cardiovascular stents. And the stents are like this. So on this rotating rod we are depositing, and we have developed our own ink that is a biodegradable material ink. I am able to deposit these kinds of cardiovascular stents, and these stents have been tested on with angioplasty system which we have taken for you. So we have done mechanical testing with radial compression and bending load testing, and also seen the jamming. Then once it will be expanded, what happens to its diameter and whether it fails or not. So we have passed all those tests. Then we have also studied biocompatibility, cytotoxicity, and cell adhesion and cell growth studies claims really on this particular stage. So these results have been shown here with the non-toxic, and they show the better cell growth, cell adhesion, marvelous stage. And this is a dynamic degradation because this particular stain will resolve in the body of the human being. So we have done this testing. These stents have been placed here in this tube, and the function of art is in it. It gives you some solution which runs at 27 degrees, and we are able to study the dynamic degradation along with the static degradation, that is the emulsion test. Different kinds of degradation studies have also been taken up by Additive. Then we have done so many other things. So this is another attempt where we have made a trachea. This is a door trachea. So on this printer, we have developed these kinds of novel tracheas for regenerative applications. They are implants basically. So even today, there is a project going on with James T. That is, we are trying to do now in vitro studies. That is, we implant rats. So that is all being done in will always come back. We just make the things and give it to them. The project is going on there. They are making these kinds of practice. This is another important work which we did at IT. So we made these kinds of foot that they have been taken from the kids who born with this kind of deformity. By MRI scans, we have developed this model and performed testing on this and developed this kind of solution that is called a prosthetic, which can be put on the foot of the baby and the defect can be repaired or it can be eliminated in very short time. And this is a device which we developed for measuring the deformity. These are few important items we did in IT. Now I'll show you one last thing. It is quite interesting. Yeah. So you can see this is the process we developed at our place. It's called independent physical. Correct? So in this gel, we are able to write in three-dimensional space. We are able to create components of polymers like this within this gel. So no support structure is needed. This is very recent work which we have completed, I think last year only. And today this is the time when we talk about Industry 4.0. So one student has done that thing also. So we have installed various kinds of sensors on 3D printers, trying to take temperature, part monitoring, vibration analysis, image analysis, and then develop machine learning models during the model regression, and finally predicted the difference of the components. And then we developed the digital twins. You might have heard about digital twins. This is the first work in India. We did develop the digital twin of FDM process. So you can see this is the actual process and this is the digital twin. So this is moving in X direction, this is the Z direction movement. This is the actual of the actual printer. The simulation नहीं है, not a simulation. It is digital twin. So it also presents the optimum parameters required and the accuracy of the component that can be obtained when you do this particular thing. That's why we have done the work. So this is the first attempt of our thing. So with this, I think I conclude here. If anybody has any question, one can ask. Thank you. Any questions? Anybody has?
No discussion, please. Please sit down. Yes, please. बंद कर देते
या ये एक सेशन था ना?
Or session recycling and enriching session related to additive manufacturing, its possibilities, applications, processes, principles, not only in the field of medical engineering, but in several other fields. On behalf of Department of Mechanical Engineering and all the participants, I express our sincere gratitude to you for sharing your valuable time, knowledge, and thank you once again, sir. May I now request may I now request Head of the Department, Dr. Mohammed Asim Qadri, to kindly present a memento to our distinguished guest, Dr. P.M. Pandey, as a token of our gratitude and appreciation. Sir.
एंड कर रहा हूँ।